Good morning. Today we'll look at one of the most misunderstood parts of an EV, the transmission and driveline. Unlike IC engines that need multi-gearboxes, clutches, and torque converters because they only work efficiently in a narrow RPM band, EV motors deliver high torque from 0 RPM and stay efficient across a wide range. That single difference completely changes how EV power reaches the wheels. In an EV, the battery sends DC power to the inverter feeds AC to the motor, and that rotation is sent to the wheels through the driveline. Because an electric motor gives maximum torque from 0 RPM and can spin up to very high speeds, EVs don't need multi-gear transmissions. Instead, most use a single fixed reduction gear, typically around 7, 1 to 12, 1 to cut motor RPM down to wheel speed and multiply torque, with no clutches or shifting. Since electric motors can provide max torque, they eliminate the need for multiple gearbox to stay in the power band. Also, electric motors can reverse simply by changing the direction of current, so there's no need for a reverse gear. A simpler transmission also reduces energy losses. Every extra gear, clutch, or synchronizer introduces friction. EVs aim for high efficiency, 85 to 95%. A simple single-speed gearbox supports that goal. That said, not all EVs are single-speed. High-performance EVs, like the Porsche Taycan, use a two-speed gearbox. Why? The first gear gives massive acceleration, and the second gear provides better efficiency at highway speeds. This is mainly for performance cars, where top-end efficiency matters. Let us break down the driveline components one by one. Behind the motor's output shaft is the reduction gearbox. This typically uses spur gears, helical gears, or planetary gears. Spur gears are simpler with moderate efficiency but noisy. Helical gears give smoother, quieter operation with higher efficiency, but comparatively complex than spur gears. Planetary gears offer compact packaging with complex assembly but provides optimized efficiency. After the gearbox, we have the differential, just like in conventional cars. It allows the two wheels on the axle to rotate at different speeds, which is essential when turning. The driveline may also include half shafts, constant velocity joints, splines, and sometimes a propeller shaft, in the case of all-wheel drive EVs with front and rear motors. But in many modern EVs, especially dual-motor systems, each wheel or each axle has its own motor. In those cases, the mechanical differential is not needed. Instead, software performs the job electronically using torque vectoring. However, because there are fewer vibration sources in an EV compared to an engine, the driveline components are often lighter, simpler, and have lower maintenance needs. Driveline layouts vary depending on motor placement. Let us look at the common arrangements. The single motor front-wheel drive. Here, the motor, reduction gearbox, and differential are integrated into a single compact unit mounted at the front. This is identical to how an IC front-wheel drive layout works, but without the clutch or multi-speed gearbox. Many EVs like the Nissan Leaf use this layout. Single motor, rear-wheel drive. Popular in performance cars and luxury EVs, the motor sits at the rear and directly drives the rear wheels through a reduction gear and differential. Because the motor is compact, weight distribution improves and traction increases. Dual motor all-wheel drive. Two motors, one front and one rear each, with their own reduction gear. No mechanical link between them. The vehicle uses software to control torque distribution. This gives perfect traction, instant torque vectoring, and better stability in all conditions. Tesla's AWD models follow this layout. In-wheel motors, direct drive. This is the most radical layout where the motor is placed inside the wheel hub itself. Here, there is no transmission, no differential, and almost no driveline. Each wheel has independent motor control, giving unmatched precision. The drawback is increased unsprung mass, which affects ride comfort. One special feature of EV drivelines is regenerative braking. When the driver lifts the accelerator pedal, the motor starts acting like a generator. It begins to resist rotation and converts kinetic energy back into battery energy. This reduces wear on mechanical brakes and significantly improves vehicle range. The driveline must be designed to handle bidirectional power flow, because torque flows from motor to wheels during acceleration and from wheels back to motor during regeneration. The reduction gearing, bearings, and joints must be strong enough to handle both directions of torque. Even though EV drivelines are simple, they still face challenges. One challenge is NVH, noise, vibration, and harshness. Because there is no engine noise, the gear whine from the reduction gearbox becomes very noticeable. Engineers must design tooth profiles and lubricant strategies to minimize this. Another challenge is high-speed operation. EV motors can spin extremely fast, so gearboxes must handle high RPM and high torque simultaneously. Lastly, efficiency is critical. Even a 1% loss in the transmission reduces EV range. So careful optimization of gear material, lubrication, and bearing selection is necessary. So to summarize, electric vehicles use a very simple transmission and driveline compared to IC engines. Most EVs operate with a single-speed reduction gearbox because the motor itself provides a wide operating range and high torque at low speed. Drivelines can be front-wheel drive, rear-wheel drive, dual-motor AWD, or even in-wheel direct drive. The entire system is designed for high efficiency, low maintenance, quiet operation, and compatibility with regenerative braking. Understanding this foundation will help us appreciate how EVs achieve smooth, instant, and highly efficient performance. Thank you. Meet you again on another topic in EV.